Hi, I'm Michael Pfeiffer, Principal Consultant and Trainer at Industrial Metallurgists. In this presentation, I'm going to discuss Six Sigma and materials engineering. This presentation is for people who are new, who want to understand what Six Sigma means, or are new to statistical process control, and also want to understand how materials engineering can be coupled with statistical process control to make improvements to manufacturing processes. So first I want to talk about and explain about Six Sigma and statistical process control, because I think the term Six Sigma is tossed around a lot, kind of carelessly sometimes, and I think people have lost a sense of what the terminology means, because the term has become kind of a marketing term, and they might not understand how it fits in with statistical process control. So Six Sigma is a reference to a statistics value that's used in statistical process control, or SPC for short. I'll be using the term SPC. And Six Sigma, the sigma refers to standard deviation, which has this the sigma as its symbol. So SPC is a data-driven methodology that's used to minimize defects and variation in manufacturing processes. And it involves use of statistical methods to monitor the ability of a production line to produce output that meets specifications. And it's also used to identify when corrective actions have to be taken to prevent producing output that does not meet specifications. And this can happen when there's a problem occurs with a manufacturing line, such as an equipment breakdown or operator error, or maybe a change in the environment. Things that cause changes to the manufacturing process that affect the manufacturing output. So one of the important calculations with the statistical process control is a standard deviation. So I'm going to talk a little bit more about that. So for any manufacturing process, we can identify either dimensions or properties or some performance attributes that we can measure in the thing that we're creating with them in that manufacturing line. And we can then plot the output, whatever the thing is we're measuring, versus the time. So each of these points corresponds to the measurement of whatever the thing that we're measuring. And we plot this over time, and then the data that we collect can then be plotted in a histogram, and we plot the number of occurrences versus the measurement value. And if it's a normal distribution or a bell curve, then we get curves such as those shown here. You've got this curve number 1, and curve number 2. So plot number 1 is for one set of data, and plot number 2 is for a different set of data. The standard deviation refers to the spread in the data. The larger the standard deviation, the larger there is a spread in the data. So if we look at data set 1 and data set 2, data set 2 has a larger spread in data, and therefore it will have a larger standard deviation compared to data set 1. And then the calculation for the standard deviation is shown here. It's equal to the square root of the sum of each individual value minus the mean. So we have to calculate the mean for all the process output, and that value is squared, and then it's divided by the total number of data points. And so using this equation, we can calculate the standard deviation for any set of data. So what is Six Sigma? Well, Six Sigma tells us is a reference to the number of defects that are present in a manufacturing line where we have where the mean plus or minus 6 standard deviations contains all of the data that for the items that's being produced. So we have the process output measurements. Again, we plot this curve, and if the standard deviation, and if we have, and there is an upper spec limit or specification limit on the thing that's being produced, and a lower specification limit. For example, if we're producing something, let's say a block of material that has to have a certain dimension, then it's going to have an upper limit on the maximum dimension it can have, and a lower limit on the dimension it can have. And then there's something called the control limits, the upper control limit and the lower control limit. And for the manufacturing process, we want to try to run the manufacturing line so that the thing that we're producing, we're measuring, it falls within the upper and control limits and doesn't come, and that we don't produce things that come close to the specification limit. We want to try to have a production line that keeps far away from the specification limits. When a process is Six Sigma, this graph shows the curve of the data, and this is the mean. If this shows the mean minus one. This point, this line right here corresponds to the mean minus one standard deviation, and this is the mean plus one standard deviation. The total amount of data that fits in here is 68% of the data. Then if we look at the mean plus two standard deviations all the way to the mean minus two standard deviations, then this consists of 95% of the data. And then the mean plus and minus three standard deviations consists of 99 and 7/10% of the data. When we look at the mean plus or minus 6 sigmas, so it's out here, somewhere out here, and somewhere out here, and look at all the data that contains, that includes 99 and 99,966 10,000% of the total occurrences. Or said another way, it means that 3.4 out of 1 million occurrences fall outside of plus or minus 6 sigma. It means that the parts are not compliant with plus or minus 6 sigma. Ideally, we have a manufacturing process set up that has a spec limits, upper and lower spec limits, and a standard deviation that result in only 3.4 out of 1 million occurrences of the thing that we're producing falling outside of plus or minus 6 sigma. So that's where 6 sigma originates from. And it's a way to indicate, if we say a process is 6 sigma, it means it only produces 3.4 out of 1 million defects, or 3.4 defects out of 1 million occurrences of the thing that we're producing. So for example, let's look at a manufacturing line that's producing this thing. It's a rod, and the requirements are that it has to be 100 millimeters plus or minus a quarter of a millimeter. So the upper spec limit is 125 hundredths millimeter, and the lower spec limit is 99 and 75 hundredths millimeter. And then these are the control limits. We want to try to keep the process between these two limits. 6 sigma means that only 3.4 items per million of this thing produced don't meet these specifications. That means that those points would fall outside of the upper limit or the lower limit. There are other parameters that can be measured. We can measure, besides dimensions, we can also measure electrical resistance, surface roughness, coating thickness, metal hardness or plastic hardness or strength, and many others. We just have to decide for any particular manufacturing line what the important properties are, or attributes that we want to measure, and then go ahead and measure those things. So statistical process control, SPC, involves a bunch of statistics calculations that includes standard deviation, CP, and CPK, and others that help us characterize a manufacturing process and monitor it to understand if it's capable of consistently producing output that meets our requirements, and also for identifying if there's a problem that is occurring with the process. One important calculation that I've shown here, and there's others that are important, is the CP. CP is the upper spec limit minus the lower spec limit divided by 6 standard deviations, 6 sigma. And this is an indication of the process capability. The larger CP is, the more capable the process is. And ideally, you want the CP to be significantly, to be larger than 1, hopefully 1.5 or even 2. And there's other people teaching things that can go into more information about CP and also CPK. So we use the CP and CPK to make and monitor process improvements that help reduce output variation. So we use the data that we collect to calculate these values and to try to figure out where there might be where there are causes of variation in the manufacturing process, and try to eliminate those causes of variation. Sometimes sometimes we've eliminated all the major causes of variation, and the only thing that's left is just random variation. We also use the process output data to identify when sudden problems occur such as an equipment malfunction or an operator error, or maybe a change in the environment or a change in the materials that are coming into the manufacturing line. And based on this information, identify the cause and then fix it and prevent problems from occurring and prevent creating product that goes outside of the spec limits. So finally, from a marketing perspective, the term statistical process control just doesn't seem as cool as Six Sigma. So people have been using the term Six Sigma. Unfortunately, by using the term Six Sigma, I think a lot of information about what that really means is lost, and people have just been using it as a marketing term without, and perhaps not even applying it internally to help them understand their manufacturing processes or other processes, and that is by using statistical process control. So Six Sigma is a fancy buzzword for marketing, but if people don't understand what it really means, then it's kind of lost its purpose, lost its value. So my first experience with SPC was at Motorola. Motorola was one of the pioneers in the U.S. with using statistical process control. They started using it in the mid 1980s, and I was working on a manufacturing process where it was involved depositing thin layers of aluminum onto silicon wafers in an integrated circuit factory. And then this shows a wafer, and then this is the aluminum after it's been etched to have formed the interconnects between the different transistors and capacitors and resistors on the wafer. So with the process that I was in charge of involved, it was called sputtering, and it involved placing the wafer inside of a vacuum chamber. And so the wafer would go up here. There was an aluminum target inside of the vacuum chamber, and the process involved igniting a plasma inside of the vacuum chamber, and we characterized the voltage, the current, the gas pressure, and the aluminum deposition rate in order to characterize the process and the behavior of the process. And with that information, we were able to develop computer control over the process variables, and that enabled us to run the process without operator interventions or operators making decisions about how to control the process. And the result was that we were able to we reduced the variation in the thickness, which resulted in a reduction in the standard deviation, which helped improve our CP. So we've developed a more capable process. So that was my first interaction with SPC. From the perspective of materials engineering, we can measure a lot of different things from a process output. We can measure dimensions. We can also measure different properties, and also measure performance attributes. And in many cases, these are related to the materials in the thing that we're producing. And so materials engineering can be very important to help understand variation in the process and to engineer the materials and engineer the process to reduce the variation. So we want to select materials that have the properties necessary to enable good manufacturability. That is, process materials that we're capable of using them to continually to reduce process variation. And this might not only mean selecting a particular alloy or a particular polymer, it may also mean selecting a particular supplier. We want to make sure that we use suppliers who are capable of supplying materials that have low variation and that continually meet our requirements. So that means reducing the variation of incoming materials. Also, we can characterize the effects of the process conditions on the material's properties and understand the relationship between the process conditions and the material's properties and how that affects the properties and performance of the thing that we're producing. We can characterize the effects of incoming materials variations on process output. Perhaps it's possible to allow for larger materials variations, without having an impact on the process output. And the benefit of that is that might mean being able to use lower cost suppliers or using different suppliers, which will help reduce the cost of the incoming materials. And we can also verify that suppliers are capable of supplying materials and components that meet specifications. And then finally, we use failure analysis to obtain information that helps us understand the root cause of problems to when the control charts show us that the process is going out of control, we can do failure analysis to figure out the root cause and fix it and prevent it from reoccurring. So these are all ways that materials engineering can be applied to statistical process control to help improve manufacturing processes. So if you're interested in learning more, we offer metallurgy courses, live short courses, videos, articles, podcasts, and also corporate training. Go to our website, www.imetllc.com, and check it out. Let me know what you think. We'd love to get your input. Thanks for watching. Bye.